Good morning, good afternoon, and good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni on Global Electronics. Yes, today is July 10th, 2026, and we are now getting after 6 months of 2026, seventh month, already 10 days have passed. Global Electronics mainly, focusing on bringing various topics on electronics manufacturing activities, whether it can be design related, whether it is DFM, DFX, process related, manufacturing, supply chain, the market intel, so on and so forth. As we all know, the electronics market is growing exponentially for various reasons. One of the main reason is artificial intelligence and data center. As the data center requirement is growing, because everywhere you need data, and the companies are putting on a lot of data centers across the globe, and the data center requires a lot of power, and power electronics means a lot of electronics, and electronics manufacturing is exponentially growing as the circuit gets dense and dense, and also thick. The power handling capacity grows, and so does the requirement of the electronics manufacturing in a very finer way. And so we bring in topic that is related to the electronics manufacturing every week, and these topics are all different. And right now the topics that we are running is a sequel on electronics manufacturing, and the title of the topic, today's topic is very unique, and that is hierarchies in off-chip, off-package HSIO connections. And yes, this is a sequel of physics-based HSIO interfacing in routing, that is episode number 6. We have already crossed 5 episodes. The 6th episode is today's. And we have, to present this, we have Mr. Ambaprasad, a technocrat, a highly rated individual, a professional engaged in design of various aspects in the printed circuit boards, in the electronics manufacturing, and he is based in the Silicon Valley or Silicon City, that we can call in India, that is Bangalore, which is southern part of India. Mr. Ambaprasad carries wealth of experience, and that's the wealth of knowledge that we are sharing with the individuals like yourself who are ready to accept those knowledge and implement on your day-to-day activities. So let's welcome Mr. Ambaprasad. Good evening, Mr. Ambaprasad. How are you this evening?
Oh, very good.
Excellent. So let us start. Yeah, go ahead.
You just now said that the enthusiasts are ready to accept whatever we are projecting.
Yes.
In fact, at the end of the slide, we are going to talk about some individuals who don't want to accept not only what we say. In general, they don't want to accept whatever is told by the industry itself. I termed them as mavericks, in the sense they can be the leading edge who doesn't follow, they don't go along with the tide, or they can be due to some reasons. They are also good actually. In the previous episodes, I told registered and non-registered outlines and MSAs and all. there are some people who don't want to follow. It's not that they're indisciplined, because they are ahead of the curve. So I call them as mavericks. So they also play a very important role. We are touching upon them also. It is not only that we talk to people who listen to us, we also want to talk to people who don't listen to us. So that's the whole idea.
Okay, let's now get on to our
Full size? Yeah.
presentation slides, and here is the presentation slide that is being displayed, and this is where we have left on the last episode. So over to you, Amba.
In the last episode, we stopped over here telling electromigration and IR drop, a package. And then the new episode, episode 6, what we're talking, I'm literally starting from the chip and going up to the what we call as a breakout or a fan out to a package, and what are the challenges they are faced. Then going ahead, we can go from the package to PCB and PCB to connector and onwards. So uh, the way we have structured this is the way the signal travels. The signal originates in the root complex at the chip, and it goes through various barriers, and then it ends in another chip. That's the total channel. So I thought, let me unravel things the way a signal goes through the whole channel. That way it makes things a little interesting. And also we'll not be telling, as we told last time or something like that. We are going in a forward path. So that makes sense. That's how I have structured this, though it may look boring, or it may look for certain category of audience, they may think that it is out of my subject, or it is, I know this already, but that's not the case. We are going the way a signal travels in the channel. Okay, next page. As usual, the title, physics-based interface routing, chip-level interfaces, hierarchies of off-chip, from the chip to the package, and then off-package from the package to the PCB, and off-board. There are three hierarchies. One is off-chip, chip to package, and package to the PCB, and PCB to the outside world. That's how it goes. And when the signal reaches the destination, the path is reverse. So from the board edge, it goes to the package. From package, it goes to the chip. Then the journey is complete. So that's how it has been structured. Okay, next page, please. Agenda, off-chip connections. In this, I'm covering only off-chip connections, though off-chip and off-package, off-board may take 3 episodes. This is in this episode, I'm talking about off-chip connections, chip to package connection mapping, hierarchy, chip to the system, off-chip, die to die, and intra-package, that within the package, how the signals move and what are the limitations. And the hierarchy standards mapping, a table I have given. May not be a complete table, but I'm touched upon, it's not a deep dive, but I'm touching on, the audience can go and search on their own. If they are following any standards, standard bodies will publish it. Or even if they are mavericks, they have enough wealth of knowledge and motivation to search it parallelly. They can do it, not an issue. We talk about the channel, we talk about the physical medium, and the key standards which are useful. Key breakout options for high-speed interfaces, I/O interfaces, off-chip, die-to-die, and within the package. Now the package, when we talk package, and packages are no more monolithic, they are heterogeneous. In fact, the IEEE classifies package from 2D up to 5.5D. So 2D, 3D. Then there are a lot of decimals. So sometimes they call 3.5D, 3.75D, 4D, 4.5D, up to 5.5D. They have a definition. Maybe we can cover that in some other forum. This is the tightest level of hierarchy, focusing on a communication between multiple silicon dies housed within a single package. The transition towards chiplet architectures and heterogeneous integration has made this tier the foundation for modern high performance computing, which includes GPUs and XPUs. That is the definition. The channel signals travel, actually a signal travels only a few millimeters within a package. That's it. That's what it travels. Then it enters the PCB. Travel a mere few millimeters within a package. The focus is on massive parallel bandwidth, ultra high density packaging, and extremely low power consumption to transfer the data, measured in picojoules per bit. So in data center, they say how many picojoules they are using to move one bit across the channel. The physical medium routing is handled via interposers, organic buildup substrates, and nowadays people are using glass substrates. Glass is gaining the traction due to its superior dimensional stability, smooth surface and fine line photolithography options, and ability to handle dense I/O requirements of advanced packaging. The key standards which are here in PCB, we use via. Here we use TSV, a through silicon via, if it is a silicon package, or we are using a TGV, which is a through glass via, if it is a glass interposer. So TGV is also a fastest moving train in the world in France. So I don't know. We can compare these two, TGV versus package, how signals move. That's not an issue. Key standards, there is a new standard which came about 5 years back. It is called as the Universal Chiplet Interconnection Express. It is called as UCIe. Already 3 revisions have come, and generally heterogeneous packaging, they use this standard. Then there are some other free standards by specific companies. One such name is called as bunch of wires. This is a standard. This is used in packaging. The design focus is minimize latency and optimize the power delivery within the package, as and when you move the data. Next page, please. This is just a schematic. I've just shown how on one side I'm showing the electrical intention, SerDes transmit, and SerDes receive. So the signal starts from the root complex. It is an output. It completes the journey through the package, through PCBs, through cables, whatnot, and then it enters the package on the other PCB, which can be a next. It can be in the rack. It can be the next PCB, or this PCB can be somewhere in the other continent. That's how much signals will travel, and then it is reversed. The path is reversed. Generally, what you see in TX, the path is reversed in the RX. Then it enters the other package. Transceiver example, ASIC or FPGA. This can be ASIC or this can be FPGA. This is just a schematic. Then physically how it looks, a cross section I have shown. IC package, they can be a die, they can be a die bump, package substrate, redistribution layer, then a BGA ball. BGA ball is the one which makes a connection between the package and the PCB. Then again, I have shown some cross section, PCB and backplane, how it looks out. And here we encounter what is called as insertion loss. We crosstalk both far end and near end, which is called as FEXT and NEXT. Then we say return loss. We see impedance mismanagement, mismatch, discontinuities, which is also considered as a noise. Then we see the physical constraints, trace geometry, dielectric material, ultra low loss, Mectron 6, 7, or 8, even Mectron 9 has come into the market. So this is how things go. Then there can be a cable, there can be a connector, there can be optical cables. This is how this is the medium. Through this media, signal is transferred. So next page, please. Here I've broken down some levels. This particular image we may even reuse in the next level also, or we may expand it further. For example, in the next level, level 2 also, I may expand it a bit and show how it looks like internally. So level 0, off-chip HSIO channel at a silicon level. Just shown a typical visual diagram. Off-chip through silicon vias are used. C4. C4 means it is a BGA ball. Okay, C4 is controlled collapsible chip connection, that is C4. The other name is, in normal English, it is a BGA ball. Okay. Then flip chip bumps can be used, wire bonding can be used. Then there are connection examples they have shown, how it looks like die to die. COVAS is a brand name, INFO is a brand name, and BOW is a bunch of wires is a brand name. EMI, IB is a brand, UCAE is a consortium. So these are the sort of jargons people will be using on day-to-day life. It can be 2.5D or 3D, up to 5.5D is available. Level 2, package to substrate to redistribution layer, visual diagram I have shown. Then here it is called as a semiconductor-like packaging PCB. Key connections, PCIe Gen 5.6, again a standard. CXL is a standard. DDR5, LPDDR, people are aware. NVMe is a proprietary standard. Ethernet is a 30-year-old standard, which is available. Level 3, from board to another board at a system level. So I have shown everything, and I have shown what are the standards that are used. I have taken some examples, but this is what it is most popularly used. But a lot of standards, legacy standards or standards under development are there. The users can use it. Generally, the chip vendors will dictate which standard to follow. That's it about this slide. Next page. Here I have shown a key difference between a HBM and an XPU. Today, high bandwidth memory is a new level of memory packaging, which is very generally used. Already, they have gone up to HBM4, HBM5, like that. And I have shown how they have done a vertical stacking here to between the CPU and the memory. But in a GPU packaging, it is a true heterogeneous packaging. There can be a CPU, there can be accelerator core, chiplets, even power management. A lot of various generation of chips are integrated into one physical package. So this is a difference. So one of them is like a multi-storied building. The other one is like a typical, what is a community built layout. So this is how it looks. These are the two differences that people should visualize. That's how I captured it. Next page, please. The key breakout options for HSIO, differences between HBM packaging and XPU. I have just captured whatever I shown in the picture. The key differences in structure, purpose, and application between HBM, high bandwidth memory, and XPU, a logic accelerator packaging used in a data center. HBM packaging focuses on a dense vertical die stacking using through silicon vias and a silicon interposer to achieve maximum memory density and bandwidth. The idea is how fast you access the memory. But in XPU packaging, focuses on a horizontal integration of a diverse chiplets, CPU, GPU, AI cores, purpose-built cores on a substrate to optimize computing performance and heterogeneous functionality. So here, for example, we had a computer, a desktop computer or a workstation sometime back, the entire motherboard, the entire workstation, what a workstation was doing, here one chip will be performing that option. Okay. So much of densification of that. So next page, please. I think here we can take a break. Here I have some numbers dropping and standard dropping I'm doing. I think this is the right time to take a break.
Okay, this is the break time, and we will see this, watch this video, and then we'll be right back. Good morning, good afternoon, good evening, and welcome back to the Global Electronics Friday Talk Show with your host Rajiv Kulkarni. Today we have Mr. Ambaprasad, who has more than 40 years of experience in the electronics design and manufacturing activities, and he's based out of Silicon Valley of India, which is Bangalore, southern city of Indian state. So we have been discussing on various topics every Friday, and this Friday we are focusing mainly on hierarchies in off-chip and off-package HSIO connections, which is a sequel of for the last 5 episodes we have been talking on physics-based HSIO interface routing, and this is the episode number 6 on that topic. So let's get back to the presentation mode, and after this small break, here we go. Yes, Mr. Ambaprasad, over to you.
Hierarchy mapping, this may not be exhaustive, but it is just on the surface I'm showing, not a deep dive. The level off chip, off package, off board. This also I may reuse in the next episode, or I may expand it a bit. Off chip die to die interposer EMIB, very short range SIDs, I told a few millimeters. Primary standard, global technical standards, which are international standards, electrical or avionics or military, space, then performance standards for reliability, design focus, interposer, signal integrity, thermal management, die attach, chiplet power integrity. Then there can be a checklist how to go about it. They do simulation, they do budgeting, then only they sign off. Off package, flip chip escape, via and package, redistribution layer, package BJ escapes, still it is used as a escape only. IPC 2226 is a standard, IPC 2221 is a design standard, 2226 is for high density standard. This is used, they define so many. Then going down further, micro via geometry, via and pad, staggered via, stacked via rules, HDI stack up, and this can be fed into the CAD package. Micro via size, aspect ratio, sequential lamination, via and plating specification, then inspection, X-ray, CT inspection criteria, all this. Off-board, PCB traces, connectors, backplanes, cables, optical connectors, optical transceivers, buffers, IPC 6012 for normal PCBs, 6018 for RF microwave PCBs, IPC 2226 for HDI section, board fabrication, reliability, dielectric loss, control impedance, connector mating, unmating cycles, impedance test reports. This is what we have to audit. Impedance test reports, insertion loss, crosstalk measurements, budget, thermal shock, connector mate, unmate cycles, conformal coating, and cleanliness records. So all these are kept. If a board doesn't work, we should start from whether the board is clean or it is meeting the impedance requirements, noise budget, and then we have to go backwards. Okay, next page, please. Key breakout options, wire bond, which is a legacy. It is still used in very low-end packages, low speed, pros, low cost, mature process, simple trace routing. Cons, limited bandwidth, less than approximately 2 to 3 Gbps. High inductance, poor SAPI for high-speed interfaces. Use case, rarely used in modern HSIO, but still used in low-speed peripheral signals, and it is also used for something like RS-232 signal or even power. In fact, for power, they don't use wire bonding. For power, they use ribbon bonding so that they have less inductance and more current carrying capacity. Flip chip escape routing, ball grid array breakouts using micro vias in HDI stackups, a dog bone fan out for outer rows, via and pad for dense central pins, micro via staggered escape, and all this can be structured in a CAD package. It's not a problem. Pros, supports up to 56 Gbps SRDs, scalable to PCIe General 5.6, CXL Express, Cons, complex PCB stackup, higher cost, requires strict DFM, strict DFX, signal integrity analysis. Best for high density, FPGA, ASIC, high speed IO, PCI, Ethernet, DDR5 and onwards. Best suited for consumer SoCs, that is system on chip and mobile high speed interfaces. Next page, please. 2.5D interposer silicon bridge. Now things are becoming a little complicated. Approach HSIO signals routed through silicon interposer on a embedded bridge. Example, Intel EMIB. The EMIB is as long as a basmati rice grain. So you can imagine. That's the people. EMIB is not very big. It is as long as a basmati rice grain. So that's what somebody said about that. It is used in ultra-short interconnects, excellent signal integrity, low loss, low jitter, supports 112 Gbps PAM4 protocol, expensive, requires advanced packaging ecosystem. Now you are getting into high-speed, ultra-high-speed ecosystem. Best for chiplet-based SoCs, AI, HPC, high-performance computer accelerators. Then next FOWLP, fan-out wafer level packaging. This is another protocol, a physical protocol, that is. Redistribution layers for signals fan out before reaching the PCB. Actually, in a PCB, we use sort of a millimeter and mils, but in a redistribution layer, we use microns. That is the only difference. Pros, thin profile, reduced parasitics, good for mobile high-speed interfaces like LPDDR. Limited board level escape flexibility, thermal challenges, best for consumer SoCs, mobile HSIO interfaces. So this is where it is used. Next page, please. Again, captured in a whatever 2 pages are captured in a table. A wire bond less than 2 to 3 Gbps. Density is low, cost is low. Legacy peripherals will not go away. They'll be there. Okay. Because of backward compatibility or heterogeneous integration. They'll be there. Some part of your IC is low speed. You cannot stop it. A flip chip plus escape, 28 to 56 Gbps, high density, medium cost, FPGA, ASIC, HSIO banks, 2.5D interposer, 56 to 112 Gbps plus, very high density, very high cost chiplets and high performance computing and AI chipsets. Fan out WLP, wafer level packaging. WLP is wafer level packaging. 10 to 28 Gbps, medium mobile SoCs. But still other standards are under the works. Maybe I cannot disclose them because I am under strict NDA with the people who are developing it. But maybe next year we can say what it is. So that's where we are. Okay, next page, please. Risks and design consideration for key breakout options for HSIO. Signal integrity, this is always a risk. Crosstalk, insertion loss, simultaneous switching noise must be mitigated with careful escape routing and termination strategies. Power integrity termination means it can be on the die or within the package. Power integrity, HSIO banks often share power supplies. Decoupling and ground return path is very critical. Whenever we do signal integrity analysis, we assume power is perfect, but if power is not perfect, if PDN is within budget, it will give a power supply induced noise. Manufacturability, a WIPO or a microwire reliability must meet IPC 6012 or 6018 standards, which is very, very strict. Thermal management, high-speed SerDes increases heat, advanced cooling may be required. So your favorite subject. This never, I think we are only hitting things now. Actionable guidance for HSIO breakout. For example, whenever I say power, I say people not only think about power, think about thermal also simultaneously. That is a power-aware signal integrity, power-aware power integrity. That's how it is. For mainstream FPGA, ASIC, HSIO, PCIe Gen 5, 6 onwards, DDR5 onwards, Ethernet 800G Nowadays, everybody is using 800G. Flip chip with WIPO plus HDA escape is more practical. For chiplet-based AI HPC systems, 2.5D interposer or a silicon bridge ensures a SI closure at 112 Gbps. And you should have a 10% to 12% of overhead. When you say 112 Gbps, if you take 12% out of it, it is 100%, 100 Gbps. So what we call as 100 Gbps, IEEE called as 112 Gbps. The 12% is the overhead, I think. Okay. For mobile and consumer SOCs, fan out WLP balances cost and performance. Next page, please. Yes. Only two more
This is
slides. I think
this
this is
is
the
great.
three more. So whenever we do a chip design or a package design or a PCB design, the industry talks of walls. There are three walls. There are a lot of smaller walls, but these are the three main walls. So this wall, one has to surmount. One has to escape, jump through these walls. Basically, they have to escape. Otherwise, they'll be doing things and they'll be reiterating or they'll be respinning, or the product will never come out. So this is what it is. One of them is called as a memory wall. Even now, the design, the, the final goal is how fast your root complex will access your memory. That's it. That is called the memory wall. Then there is what is called as a power wall. So the power wall, power supply has to be very efficient and you have to use less power. However, power means, I should say, thermally aware power. So this wall is getting heated up. You can see that. In fact, they are putting a heat sink on the wall and a lot of fans they have put. And again, there is what is called as, this is a very interesting one. This is designed for cost. If we spend too much time and effort on developing a chip or a system, there is a BOM cost, there is a development cost, there is a R&D cost. So that we have to recover. We have to amortize that. Otherwise, it won't work. Then if things become too costly, there can be always a second person who can give you, say, 70 to 80% of the performance at 50% discount. Then people will jump for it. So these three walls are very much important. These three walls are, they're tightly integrated. So I just mentioned what is the advantages of the wall, and you can see some persons are sitting and working how to solve the problem. That's what it is. Now let's go to next page. Here I have told the key takeaways, three critical constraints in GPU packaging design, or any, even for that matter, CPU or memory module or anything. Memory wall, bandwidth and latency bottlenecks, which we have to surmount. Power wall, thermal and power distribution network limits and budgets. Design for cost wall, economic and manufacturing constraints. These conceptual walls represent the engineering and economic barriers that must be navigated to scale performance in next generation package. Okay, next page, please. This is where I told about Mavericks. So, how to surmount the wall, the three walls, whenever we say MSA, a multi-supplier agreement or a standard, they are little, because of interoperability and things like that, they are always, you can say, they are normal. It is like traveling in a commercial aircraft. Everybody will go together and interoperability. They are not, sometimes they are slightly behind the curve, or they are at the top of the curve. They are not very aggressive. But these Mavericks are very aggressive. They want to do it fast. They want to do it now. Sometimes it works, sometimes it doesn't work. So here, if the Mavericks say, I don't want to follow, I'll take my own path, they may not follow the standard, or they may follow the standard partially, or they may follow whatever they think is right. This is what it is. They're there in the industry, no problem. This is the challenge they face. It is very interoperability failure I have captured, non-standard form factor. System cannot coexist with other systems. Then thermal runaway, the things may get suddenly heated up. Signal integrity chaos. Because we are not following standards, we may get into some trouble. Then If we're not following multi-supplier agreements, there can be a supply chain risk and supply chain disruptions, which is happening nowadays. Really, it is there. But believe me, mavericks are there. You cannot escape them. They are there. They are following. But still, now the industry has come out. There are standards. There are standards which are controlled by a few very closely knit group of persons. They are half mavericks. They're not full mavericks. They're compliant, half compliant, or half mavericks, but they're there. That's how it is. But mavericks can they pay a heavy price to surmount a memory wall and power wall, and it is very difficult for them to come out of this design for cost wall. So that's why following a standard makes sense, though sometimes it is may not be fashionable or may not be romantic to follow a standard, but by following a standard, any standard for that matter, we can surmount the wall. That's my message.
Wow.
This is the last slide.
This is absolutely brilliant presentation, Mr. Ambaprasad. And if any audience out there, if they have any questions, they can definitely shoot any questions right now, or you can also send the questions via the YouTube link that we have posted there, because that is another way of we getting back to you after we study the question and come back. So today's episode was basically titled Hierarchies in Off-Chip and Off-Package HSIO Connections from the sequel that we have been carrying on, physics-based HSIO interface routing, and this was episode number 6. So Ambaprasad, tell me one thing, are we continuing on this sequel next week as well, or we are taking a different topic?
No, I'll continue the way I projected. That makes sense, because if people see this episode one after another, it's like a live textbook for them. They can enjoy.
Exactly.
So,
that's what I was thinking. If we keep continuing this sequel, that will help the audience who are following this particular subject, and they can follow it one after another, as you are saying, chapter 1 to chapter number of whatever chapter is. So we can
one is in August. I'm traveling heavily for this.
We'll come to August later. So can we move on to the episode 7?
Yes.
Can we move on to the episode 7 next week?
Yeah, we can move, no problem.
Okay. So with that, the audience, just make a note of it. So we will continue with the episode number 7 on this particular sequel coming week, which is July 17th at the same time. Till then, please take care. Take care. Yeah.
One thing, in world radio programs, Radio Ceylon, they used to say, Aji ke din, Aji ke samay. When the TV came, they used to say, Aji ke din, Aji ke samay, Aji ke channel. So what it translates for the benefit
That's
of
fine. That's fine. I mean, we are talking here.
Same time next week.
Yes, Mr. Ambaprasad, we are talking globally here. So please, there are many people who may not understand the local Indian language. So the people who are watching elsewhere in the world, besides US or India, so thank you very much for joining our channel, and please do continue watching our channel, and please do subscribe, and we will see you next week at the same time with your host Rajiv Kulkarni on Global Electronics, and Mr. Ambaprasad presenting episode 7 of the sequel that we have been carrying on. Till then, please take good care of your health. As we say, health is wealth. Thank you very much and take care. Have a wonderful weekend.